Okay. Hello, everybody. First of all, I would like to thank the organizer for inviting me to give this talk here in this conference. I'm only afraid not to be a nice place of Cadiz. So my talk will concern the some recent advances in the numerical solution of fractional differential equations. So this is a list of the collaborations for this research. Kevin Barrage from Brisbane, Gianmarco Gurioli from Florence, and a long-lasting collaboration with Felice Ievernaro from the University of Bari. So this is the overview of my talk. We shall speak about fractional differential equations, and we shall derive numerical methods for their solution by considering a local Fourier expansion of the corresponding of the vector field. And this expansion, this local expansion is tailored for a graded or a uniform mesh, depending on the needs. And this will lead us to define fractional Hamiltonian boundary value methods. We shall see that the actual implementation of the methods depends on the choice or proper choice of some parameters, and we shall see something about this fact, and we shall also present some numerical tests to confirm the potentialities of the approach and a few concluding remarks. So fractional differential equations are nowadays used in very many applications in very different settings due to the fact that the non-local properties of the operator allows for a more to take into account of memory effects. So we shall then consider this fractional differential equation, where alpha is in between 0 and 1 without losing generalities, and moreover, if y alpha is the Caputo fractional derivative of the function of the non-function y. Without losing into in generality, we shall just to have a more compact notation, we have omitted to put t as a formal argument of the vector field f. As is well known, the solution of this problem is given by if we integrate side by side and impose the initial condition, is given by y naught plus the Riemann-Liouville integral of f of y of t, which is defined this way, as is well known. Clearly, alpha here is the same parameters appearing in the fractional derivative. And the approach we shall use to for solving this problem is totally related to the one we have used in devising in the ODE case to derive Hamiltonian boundary value methods, or in short HBVMs, which consists in expanding the vector field along a suitable orthonormal polynomial basis. The approach concerning this approach, I can refer you to the 2016 book by Felice Ievernaro and myself. So the basic idea is quite straightforward. Let us consider, for the sake of brevity, and because we are speaking about one-step methods, about the problem defined on the interval 0h, where small h is the time step we want to use. Then we can rewrite the problem in this form, and this is the initial condition. If we consider the expansion of the vector field along this orthonormal, the orthonormal Legendre polynomial basis, then we formally derive that the vector field can be written as this infinite expansion along the Legendre basis in terms of the Fourier coefficients that, because due to the fact that the basis is orthonormal, do have a very simple expression, namely this integral. Then if we integrate side by side the differential equation and impose the initial condition, we have that the solution has this expression, again, given in terms of an infinite series. Now, the basic idea is quite straightforward. In fact, if we want to derive a polynomial approximation to this, to the solution y, it is enough to consider a truncation of the previous infinite series to a finite sum with S terms. So here we have a sum with S terms, again, along the Legendre basis, in terms of the Fourier coefficients gamma j of sigma, which are do have the same expression as before by formally replacing y with sigma. Again, if we integrate side by side, we obtain that the approximation, which now is a polynomial of degree S, has this very simple expression. Moreover, if we approximate the Fourier coefficients by using a Gauss-Legendre quadrature of order 2k, so with ways Ci, Bi, and abscissa Ci, we eventually arrive to a k-step Runge-Kutta method, k-stage Runge-Kutta method named Hamiltonian boundary value methods with parameters k and s. In short, HVDM KS. Now, this idea can be expanded, can be generalized to the case of fractional differential equations. As a matter of fact, now, in fact, we consider the expansion of the vector field. I remind you that now we have the alpha fractional derivative, and instead of using the Legendre polynomial basis, now we use this orthonormal polynomial basis made up of Jacobi polynomials with this alpha, which is the same used for, which is the same parameter defining the fractional derivative. So we have that the integral of the weighting function is 1, and moreover, when alpha equals 1, namely when fractional derivative becomes an ordinary derivative, this becomes exactly the Legendre polynomials, and then we go back to the case we saw before. Now, as before, then we consider the expansion of vector field that has considered for at first the first subinterval 0 h with small h its width. And then we have that the vector field can be expanded along the Jacobi basis in this way with gamma j o y, the corresponding Fourier coefficients, which do have this straightforward expression, again due to the fact that the basis is orthonormal. If we integrate side by side and impose the initial condition, again we obtain that the solution has this formal expression. And in particular, when C equals 1, due to the fact that due to the fact that the Riemann-Liouville integral of Pj01 equals 0 whenever j is greater than 0, then we have that y at h equals this expression, and this in turn is y naught plus the Riemann-Liouville integral of f of y of h, which is exactly the formal expression of the solution at t equals h. Now we do the same procedure as before. Then we truncate we truncate the series to a finite sum, and where now we have the Fourier coefficients gamma j of sigma defined as before, with sigma in place of y. And if we integrate side by side and impose the initial condition, we obtain that the solution at this formal expression. And in particular, at c equals 1, we have that c of h equals this expression, which is y naught plus I half, the Liouville integral of f of sigma of h, which now is no more the formal expression of the true solution due to the fact that the fractional derivative now is no more f of sigma, but is a truncated series. So this is only an approximation. This approach has also a very simple variational expression interpretation, which was already made for Hamiltonian boundary value methods. In fact, if we look for the expansion of the approximate fractional derivative in this form with gamma j unknown coefficients, and we impose the residual B orthonormal to all polynomials of degree s minus 1, then we can impose the L2 orthogonality with respect to the Jacobi basis, and this leads us to this expression for the coefficients gamma I, which is exactly the expression of the Fourier coefficients we devised previously. Now, let us extend the approach to the whole interval 0 capital T. And to do this, we consider a partition of this interval made up of points Tn, or n ranging from 0 to capital N, with T naught equal 0 and T capital N equals capital T, and the width of the nth subinterval Tn minus 1, Tn being Hn. And for Hn, we assume two possible choices, depending on the value of this parameter R. The first choice possibility is that of choosing R equals 1, which corresponds to the case of a uniform mesh, because all the time steps are equals to H1, which obviously equals in such a case to capital T over capital N. Differently, we can choose R to be greater than 1, and in such a case, we have a graded mesh. Clearly, a graded mesh is to be preferred when we have that the vector field is not smooth at the origin, as it may happen for fractional differential equations. Vice versa, if the vector field is smooth also at the origin, then a uniform mesh could be also appropriate. Moreover, as we shall denote by yn of chn the restriction of the solution to the subinterval Tn minus 1 Tn, and similarly we shall denote by sigma n of Chn the restriction of the piecewise approximation to the same subinterval. Now, let us see what happens. In fact, by using the previous notation, we can rewrite the original problem in this way. So here we have only local problems which are defined on the nth subinterval. So what it is, this problem is defined for C in 0, 1. That means that the argument is in Tn minus 1 Tn, and the corresponding vector field is evaluated in the same restriction. Again, we can expand this vector field along the Jacobi basis and in terms of these Fourier coefficients defined as before, but only involving the local restriction of the solution. Clearly, the initial condition is given for y1 at 0. So we can then consider the piecewise approximation to be defined in a similar way, because on the nth subinterval, instead of having this infinite series, we have a finite sum with S term, with the first S Jacobi polynomials, but now the Fourier coefficients, again involving only the local approximation, only the local restrictions, are defined by the approximation and not by the solution, of course. And clearly, the solution is given at the initial point and is, again, y naught. So now, for t equals tn minus 1 plus chn, which means t in the nth subinterval, we have that y of t, which equals yn of chn, as this formal expression. So this is the formal expression of the solution. And here we have expanded the expression of the Riemann-Liouville integral that we can decouple in as the sum the first n minus 1 subintervals plus the last piece, namely the one from tn minus 1 up to tn. Then by change of variable, if we consider, for example, the graded mesh, we can transform this into this, and this transform the global solution into the local one. This for all the sub-intervals to nu minus 1 to nu, and also for the last subinterval. And once we are able to solve this problem, so as is clear, we have that, so let us rewrite this, the last expression. And as is clear, this vector field evaluated along the local restriction of the solution, here and here, can be expanded and coincide with the corresponding vector fields of the problem rewritten in piecewise form. And as is clear, in the n subinterval, this information is already known and is constitutes this memory term, plus this additional term, which involves only the local approximation. In particular, when c equals 1, we have that yn of hn equals this expression, so the memory term, plus this Riemann-Liouville integral. And in case of a uniform mesh, namely when r equals 1, we obtain a similar expression, but with the only difference that now all hn equals h1, which equals capital T over capital N, and r equals 1. Now, in order to derive the piecewise approximation, it is enough to truncate this infinite series to finite sums, as we said before. And in so doing, we obtain that sigma n of c hn equals the same expression we saw before, with the only difference that now we have truncated sums with S terms involving the Fourier coefficients of the piecewise approximation. This is already known because this sum is up to n minus 1, and this is the last piece. So now, again, we have a memory term involving already known quantities, plus a local term in the involving only the restriction in the interval Tn-1, Tn. And again, this memory term now has been marked with this upper index S to denote that such sums only contains S terms. Again, at C equals 1, we have that the approximation has this expression, pretty similar as before. And in case a uniform mesh is used, we have a similar expression, so very similar. Truncated memory term, or sorry, this should be a sigma, plus a local term. However, this is not yet a numerical method. As a matter of fact, let us rewrite the approximation in the interval Tn-1 Tn, and let us denote in this way the memory term, which is a shorthand for the complete expression, plus the local term. Now, the problem is that we need to approximate these Fourier coefficients. And if we do this by using a Gauss-Jacobi rule of order 2k, Jacobi rule with the same alpha, then we have that this Fourier coefficient is approximated by means of this quadrature. And this, in turn, requires only to evaluate this approximation not for all C in the interval 0, 1, but only at the abscissa Ci of the quadrature. If we cast this problem in vector form, if we define this vector bold y containing the restriction of the approximation to the evaluated in the Gauss-Jacobi abscissa, and this bold phi containing the corresponding memory terms. These are the abscissa and the weights of the quadrature. Omega is the diagonal matrix made up with the weights of the quadrature on the main diagonal. And then we have that PS and IS alpha contains the Jacobi polynomials evaluated in the abscissa and the corresponding Riemann-Liouville integrals. And in so doing, we can rewrite the discrete problem in this way. Capital Y equals this vector that now we shall denote by y1, yk, equals this expression. This with the new approximation given by sigma a n of hn, which has this expression involving only the vector field evaluated in this, which are the stages of a Runge-Kutta type method, whose Butcher tableau is this one. So this is the vector with the abscissa, the vector with the weights, and this is the Butcher matrix. Now it happens that when alpha equals 1, the previous Butcher tableau exactly becomes the Butcher tableau of a HBVM KS method. For this reason, we have named such methods fractional HBVM KS method, or in short, FHBVM KS method. Now, let's come back for a moment to the discrete problem, because we know that for a k-stage Runge-Kutta method, the discrete problem has block dimension k, which is the number of stages. And we want to use a large value of k because we want enough accurate quadrature. But the larger k, apparently, the larger the dimension of the problem, the more costly the application of the method. However, this term here can be seen to be PS transpose omega tensor the identity f of y can be seen to be the block coefficients of having block dimension S with the approximate Fourier coefficients. And this in turn, if we combine the two equations, allows us to write both of them in this way. Gamma equals this. So this is actually both y. And which means that we derive an equivalent discrete problem which has block dimension S independently of the number of stages of the Runge-Kutta method. And this in turn allows us to use accurately enough quadrature rules. And for this reason, hereafter we shall assume that K is greater than or equal to S. And if we do this, if we denote by En the maximum error in the nth subinterval of the considered partition, then we have that En can be bounded in this way, depending on the fact that we use a graded mesh or a uniform one. Let us start the case of a graded mesh. So in such a case, we have that H1 is the smallest time step, the initial one, whereas H capital N is the final one, which is the largest one. So at the beginning, where the vector field is not smooth, we have a tiny time step power to alpha, plus an error term, which is Hn power S plus alpha. In case we have a uniform mesh, the vector field is smooth everywhere, and we have that the error can be bounded as n times h1, the initial time step, which is uniform, power s plus alpha. So the k idea now is that if we choose k greater than s much greater than 1, then we can expect to obtain a spectral accuracy in time. This, in turn, will allow us to use small or moderate values of capital N, which means that for an integral equation, we have a relatively cheap procedure. So now the problem is how to choose between a graded or a uniform mesh. We said that a graded mesh is appropriate when the vector field is not smooth at the origin, whereas a uniform mesh is appropriate when the vector field is smooth everywhere. And but how we can decide this in an automatic way? We choose to follow this procedure, which describe an implementation of the methods described in this paper submitted for publication. And so in the code we devised, the only input parameter is capital M, which is an integer, such that H max, which is capital T, which is the width of the interval over capital M, is roughly speaking the larger time step we want to use. So at first we initialize the first time step h1 to be equal to h max. Then we compute an approximation to h1 by using just one step and two steps with this partition 0 h1 over 4 and h1 over 4 h1. So clearly, the second approximation is more accurate than the former one. Then, if the two solutions significantly differ, so that means that the computed solution is not spectrally accurate. In such a case, we divide H1 by 4 and come back to step 2. And repeat this until this is no more satisfied. So that means that we decrease the initial time step until we have a spectrally accurate first approximation. After we exit from here, H1 is given. And in such a case, we choose capital N and R such that H1 times this equals the width of the integration interval, and such that the last time step is approximately H max, which is capital T over N, capital N. So I do not give more detail on this. It is described in this paper. Clearly, if the check at point 3 is immediately false, so that means that we can use a uniform mesh, and actually we do this. So the previous strategies have been implemented in the MATLAB code FHPVM, which make an automatic detection of the mesh and of its parameters, namely H1, R, and capital N. And moreover, the code implements an FHPVM 2220 method. So K22 S equals 20. So that means that we look for a spectrally accuracy in the computed solution. Moreover, if required, a global estimate of the error is computed. So the code is available here. And this is the code, and these are the 4 examples presented in this paper. And this is the initial paper where the analysis of FHBVM is given. And we now show the results of the first 3 examples. The first one is very well known, is a popular example, which the solution is not smooth. Choose alpha equals 0.3. But the vector field is quite smooth, actually. So that means that a uniform time step is appropriate in such a case. So R equals 1. And actually, FHBVM is able to recognize this. We compare the following 2 MATLAB codes. Codes FLMN2 implemented a BDF2 method written by Grappa, using these time steps, 0.1, 2 to the minus 2, for no ranging from 1 to 20. So that means that we decrease the time step and code FHBVM with parameter capital M equals 2, 3, 4, and 5. Then we compare the methods by computing the corresponding work precision diagram. Namely, we have a plot where the execution time in seconds is plotted against accuracy. This latter is measured in terms of mixed error significant digits. This is the expression. Roughly speaking, this is the number of correct digits in the solution. So this is the work precision diagram for this test. So this is FLMN2, and this is FHBVM. So we go from 10 to the minus 2 to 10 to the 3 seconds. And here we go from 2 to 16 significant digits. So you can see that FLMN2 is able to approximate compute 11 digits and a half in roughly 20 seconds. then even though we decrease the time step, the error increases because the round-off error increase. With the FHBDM code, we see that the error is always very small. We have in the range of 13 to 15 and a half digits, and the execution time ranges from 2 to 0.2 up to 0.04 seconds. So we have 5 digits of accuracy in more with a much more efficient numerical procedure. The second test problem is linear. This is E05 is the one parameter Dirac-Leffler function. And this is a stiff problem. This linear. The solution is not smooth at the origin, and the same is for the vector field because it is linear. And we also have two different speeds, modes in the solution, going to 0 to different speed, because here we have minus 50 and this minus 1. This is the reason why we choose the time interval to be 0-20 to have enough time for the slowest components to decrease. We compare the methods again with such coefficients, and what we get now is this work precision diagram. Now, FLMM2 stagnates at about 5 digits and a half by taking 100 seconds. On the other end, we have that the FHBVM code has always the same accuracy, more or less 13 significant digits, and the execution time is uniformly about 1 second. So again, a great improvement. So almost 3 times the significant digits and 100 times faster. So the last problem we consider is this one. In such a case, the solution is and the vector field are both not smooth at the origin, and we use the HBDM code by this parameter capital M equals 2, which produces a graded mesh with 41 mesh points with an initial time step which is very thin, of the order of 10 to the minus 12, and the last time step is about 1/2, 0.49, as we expect. And now the continuous line is the true error in the two components, and the crosses and the dots are the estimated errors for the two components. And as you may see, they agree quite well. So this just to confirm the effectiveness of the error estimation. So just to conclude, we've seen how effective step-by-step procedures for solving systems of fractional differential equations can be derived by considering a truncated expansion of the vector field along a suitable Jacobi orthonormal basis. The Jacobi basis is defined in terms of the parameter defining the fractional derivative. This approach is just a natural extension to the fractional, to the FDE case of the procedure we used formally to derive HPVMs in the case of ordinary differential equations. For these reasons, the methods have been named fractional HPVMs. We have also sketched corresponding implementation strategies default methods. And we have seen that the first release of a code implementing a spectrally accurate method proved to be very effective on some numerical tests, which are very relevant. We plan to extend the approach to the case in several directions. For example, for handling the case where in the system of fractional differential equations, different fractional derivatives occur. And that's all, and I thank you for your attention. Thank you.